There we go. Okay, so welcome everyone to the first GPI seminar of 2019. And to kick things off, we're very happy to have Sung-Sik Lee from some superposition of McMaster and Perimeter telling us about his work on quantum renormalization group and holography. So Sung-Sik, thank you very much and take it away.
Okay, thank you for joining everyone. This talk is based on a few references, but the main ones are listed there. This is on quantum renormalization group. So ADA-CFT correspondence conjectures that quantum field theory in d-dimensional space and time is due to gravitational theory in one higher dimensional space and time, and the conjecture has been well tested for certain supersymmetric field theories, but we believe that the principle behind the correspondence is general, and if that's the case, we would like to understand the principle well enough that we can derive holographic duals for general quantum field theories, and for that we would like to have some first principle derivation. And in general, holographic duals for general QFTs is not going to be simple. They can be highly quantum. However, we still want to understand the precise mapping, and hopefully that will give us a better understanding of the duality itself as well. From early on, people realized that radial direction in the bulk corresponds to a length scale in the RG sense of the field theory, and therefore the radial evolution of the bulk degrees freedom corresponds to some kind of RG flow of the boundary field theories. However, this connection between RG and the gravity is not complete because in RG, the beta function is a classical first order differential equation. So if you know couplings at a given UV scale, then couplings at lower energy scales are determined without any uncertainty. On the other hand, in gravity side, for finite n, bulk variables are quantum variables, so they will have intrinsic quantum fluctuations. So therefore, if we want to make a precise connection, perhaps the renormalization group should be promoted to a quantum version of renormalization group. So this talk is about that. And there are also many other related works, and sometimes people assume that there is a holographic dual for some field theories and try to read renormalization group information from that holographic dual. But here, our approach is to start from field theory and try to construct the bulk theory from a first principle construction. So first, I will explain what quantum RG is, and the way I present quantum RG today is a little bit different than what I originally thought about it, but I think that's clearer logically, and hopefully it makes it easier to understand it. And then I will discuss some applications of quantum RG as time permits. So suppose we have say Euclidean field theory whose action is S of phi, and phi is the fundamental degrees freedom of the field theory. And then here, as a first step, I would like to introduce a quantum state defined on the same space dimension as the field theory is defined by promoting e to the minus s, the Boltzmann weight, to a wave function. And here, ket of phi, this is some basis state defined in d-dimensional space and time. So here I'm just promoting this e to the minus s as a wave function, and this state is different from the usual quantum state. Is defined on a spatial slice, d-1 dimensional spatial slice. But here, this state is defined, is kind of space-time state, so defined in a space-time where the Boltzmann weight itself become a wave function. So it's just a mathematical object for now, but it will be useful a little bit later. And then here, phi is just a basis vector, which is labeled by different space-time configuration of the fundamental field phi.
And the path integral is over like Euclidean half plane, or
no? This is everywhere on space and time.
Everywhere.
And yeah, everywhere in space and time. And this e to the minus this e to the minus s itself is the wave function.
Okay, so sure, yeah. No, I understand. Okay.
Okay, yeah.
And sorry, like one more question. So like, but this wave function is real, right? So like that's like a very special set of wave functions.
Depends on whether the action is real or complex, but it can be complex in general.
Okay. So you don't make a choice yet.
No, yeah.
Okay, good.
So then suppose my field theory has certain set of symmetry, then the most general action that I can construct can be written as sum of operators which respect the symmetry. So O squiggly O sub m represent set of symmetry allowed operators, and Jm represent the source for that operator, and then action is just sum of those operators. And in this sense, the state that I just introduced is labeled by the source or couplings of the field theories. Okay. And then now we can think of space of field theories within certain symmetry class. But since I associate a quantum state to each action, I can interpret the space of quantum field theories as a Hilbert space. So, and in order to define a Hilbert space, we should define an inner product. So inner product is defined in the following way. Suppose I have a state ket S naught associated with action S naught. And if I have another state for action S1, then the inner product between these two states is simply given by the generating function or the path integration of the fundamental field in space and time with action S0 plus S1. Okay, more precisely, S1, S0 star plus S1. Okay. So this and this follows from the inner product on the basis state phi. Okay. Now, once we view the theory spaces, the theory space of quantum field theories as a Hilbert space, it's natural to invoke the linear superposition principle to represent general states as a linear superposition of some basis states. Okay, and one can ask what are the minimal set of basis states which can span all other states in the space of theories. And it turns out that those basis states have only a subset of operators. So the wave functions for those basis states include a very special set of operators, and they are called single trace operators. So single trace operators are defined to be the minimal set of operators where or other symmetry allowed operators can be written as polynomials of those single trace operators. So for example, here, as this squiggly O of M represents the symmetry of the theory, and then we choose the set of single trace operators, this O of sub n, such that all such general operators can be written as polynomials of the single trace operators. And in matrix theory, like Yang-Mills theory, large N Yang-Mills theory, the single trace operators are literally those operators that involve one trace. But one can define the set of single trace operators in any quantum field theories.
So say I have like a basic question. So was it? I'm like, is it something that people have done to a large extent? Say, take like a quantum mechanical problem, say harmonic oscillator, define a path integral for harmonic oscillator, and this defines for you like a wave function for a field theory, right? I'm like following your logic, basically.
So we interpret the action as a wave function.
Yeah. I understand this. Right?
Yeah.
Like, but was it done like say for one-dimensional field theories from the point of view of quantum mechanics? And like, is it something that you should consider, one should consider standard, or like, because it looks to me quite original.
Yeah, I think people have considered some types of wave function which can be written as exponential of some local functional. There are some special types of wave functions, and people have studied those wave functions like Lipschitz wave functions, but they are kind of defined on a space slice. But here, I think the difference is that is on space-time wave function. But it's just it's a convenient mathematical language to understand the renormalization group actually. Yeah.
And what happened? What happens with, say, double trace operators and so on and so forth?
Yeah. So double trace operators are not in the single trace operator, because double trace operator can be written as a quadratic function of the single trace operators, right? So the state that include the double trace operator in its wave function is not one of those basis state. Okay? And those state can be written actually as a linear superposition of those basis states that include only single trace operators.
Okay, super. Thanks.
Yeah. So here, what I have done so far is just identify the space of quantum field theories as a Hilbert space, and then identify the basis state which span the full Hilbert space through linear superposition principle. And then the claim that one can prove is that those basis states include only single trace operators. So more precisely, here the J, the cat J, is a single trace operator. The quantum state whose action include only this O sub n, the single trace operator, and this little j is the source for the single trace operator. And this state, this basis state, is labeled by the source for that single trace operator. And then mathematically one can easily show that general state like this, which includes not only single trace operator, but double trace or higher trace operator, the polynomials of those single trace operator can be always written as a linear superposition of those basis state once you choose the wave function psi of s appropriately. And then of course this wave function is a wave function defined in the space of single trace source. Okay? So so in this sense, the wave function, the actions that includes only single trace operators form a complete basis in the space of quantum field theories. Okay, now what is the connection of this object to real physical object? So then suppose I have a quantum field theory and I want to apply understand the what happens to the field theory at long distance scale. Then we usually apply the coarse graining procedure, renormalization group procedure. And when we do that, the first thing we do is to split the action into two parts. Here, split the action into S0 and S1. Here, and S0 is a fixed point of the field theory, of the theory, to which the full theory may or may not flow into. But usually we first guess what the IR fixed point might be. And S0 is our guess. And then everything else, the deformation away from the fixed point is written as S1. So usually in perturbative RG, one chooses S0 to be non-interacting action, and S1 includes interaction. This is very specific choice. But in general, we can view a general quantum field theory as a deformation added to some fixed point action. So here, S0 is one such fixed point, and S1 is a deformation away from the fixed point. Okay, that is just this line, and this generating function is given by path integration of the whole action. And then now, in terms of this state language, this generating function can be now viewed as an overlap between these two quantum states, where S0 star is a quantum state whose wave function is e to the minus S0 star, and S1 is a quantum state whose wave function is e to the minus S1. Okay, so here the generating function or partition function can be viewed as a overlap between a quantum state associated with a fixed point and a quantum state associated with a deformation. And then what is coarse graining? So coarse graining is some operation we apply to action that includes dividing some fast and slow mode and integrating out the fast mode and rescale your field and scale. And actually these processes can be viewed as some quantum operator acting on this state associated with the action. So here H represent a operator acting on this state which generate the coarse graining. Okay, and because S0 is a fixed point, S0 is invariant under the coarse graining. So in other words, S0 vanishes when this coarse graining operator H is applied on the right. Okay, so therefore this overlap between S0 and S1 is invariant under the insertion of this coarse graining operators. Here, dz is an infinitesimal parameter that parameterize increase of the length scale, and then H is a quantum operator that that generate the coarse graining. So I will give a more explicit form of such operator in concrete example, but here the claim is that this coarse graining procedure can be captured by a quantum operator acting on state.
Is it clear that H hat has a spectrum bounded from below, that it's like a reasonable, say, Hamiltonian operator?
Okay,
maybe
so
I'm just wondering.
Yeah, so that I think depends on your coarse graining scheme. But in many examples, they are bounded spectrum from below, and in general they are not Hermitian. So H and H dagger is different. But in some cases, they are related to a Hermitian operator through a similarity transformation, so that they actually have real spectrum, although the Hamiltonian the operator itself is not Hermitian.
Oh, okay. Okay.
So although the fixed point state S0 does not evolve under the coarse graining operator, that's why this overlap is invariant. But when this coarse graining operator acts to the right S1, then it generate non-trivial flow of the state. And then this new state that you obtain after this coarse graining includes some new term in the action. So that's what is written as S1 plus delta S1. And then this describes how the deformation flows under coarse graining, right? So for irrelevant deformation, that will flow back to zero, and if it is relevant, it will flow away from the fixed point. And then you can keep inserting this infinitesimal coarse graining operator between the sandwich, and then in general that describes how the action flows evolve under coarse graining. And here that defines the flow of the action in the space of theory, and that is the RG flow. So for example,
I still have a question about this transparency. Thanks. So I thought that like Z would be like invariant under the RG flow. So I always thought that Z is like some physical object. And
yes.
There's a path integral, and in this path integral we have to UV regularize it. So
yes.
The couplings that depend on the scale, right? And like the
yes.
RG, how these couplings change with the scale, right?
Yes.
So I would say that in the last expression that you gave on this slide, I would have this insertion of e to minus. Oh, but you're saying that H is going to annihilate. Okay, no, good.
Yeah. So you're right. The partition function being a physical observable is independent of this Z.
It's gonna be right, because like the H hat acting on the left is gonna annihilate S0, right?
Yeah, that's right. Yeah.
Okay. So this is what you do. So but now what you want to do is you want to see it as H hat acting on the right.
Yeah, that's right. Yeah, that's right.
Yeah, sorry for breaking you. Yeah,
that's right. Yeah, that's the point.
Okay.
And then now the RG flow is defined by how this state S1 evolve under this evolution operator. And here is just one of the simple examples. So in the perturbative RG, one usually choose S0 to be the quadratic term in the action. Here, G inverse lambda is the regularized kinetic term with some smooth cutoff with cutoff scale lambda, and then S1 includes 5-4 term or in general or high order infection, and then there's exact Polchinski RG equation that tells you how S1 evolves, and that flow can be actually exactly reproduced in terms of this coarse graining operator H, which is written in the line below. So here there's some. So here pi is the canonical conjugate variable of phi, and this is kind of corresponds to the pi square term corresponds to operator that essentially integrate out some fast mode or lowering the cutoff scale lambda, and then the second term here corresponds to the rescaling of the momentum, dilatation, and rescaling of the field itself. And one can easily check that the exact RG equation for delta S1, say in this example, is exactly reproduced by this quantum evolution acting on this state.
So, sorry, can you once again explain the first term in the last expression? So like this containing pi squared.
Yes. So this G tilde change of that kinetic term in the quadratic action. So this first term is basically corresponds to integrating out the fast mode. Okay. So what one usually do to derive the exact RG equation is to one lowers the cutoff scale lambda to slightly smaller value, and then ask what quantum correction one should add to reproduce the original partition function. Or another way of saying that is divide the mode between lambda and lambda minus d lambda, and essentially integrate out those modes within the thin shell. And then that process generates some new quantum correction, and that term is generated by this first term, the pi squared term. Okay.
So basically, what you're saying is that this first term is gonna do some addition to the action, and the second term, so the one with d plus 2 and so on and so forth, is the one that rescales lambda back to the
rescale the field. So this guy rescale the field.
Okay.
And
okay.
the last term is rescale the momentum.
Okay. Oh, okay. Yeah. Okay. Now I see it. And this phi hat and pi hat, shall I think about it as a Fourier transform of the operator defined on the full space-time?
That's right. Yeah. That's right. Yeah.
Okay. And this is valid only for this is only for free theory, right?
No, S1 includes. So here the quadratic action is chosen to be the fixed point. So here is a Gaussian fixed point is S0, and then S1 includes all interaction, all deformation. So the full theory is interacting theory in general. Okay. And then this flow generated by this H describes how all the deformation added around the Gaussian fixed points flow under the coarse graining.
Okay.
Yeah.
So you do not generate further non-Gaussianities, or you do?
If S1 was 0, then it remains Gaussian. But in general, if S1 had an interaction term, quartic term, for example, then under this coarse graining, it generates a high order interaction term. Okay,
but H is still quadratic.
H is quadratic, but in the presence of interaction, S1 includes quartic interaction, for example. So if S1 is say 5 to the 4th power, then after applying this Hamiltonian, you end up generating 6th order coupling. So as usual, under coarse graining, you generate all sorts of operators that are symmetric.
I see. Yeah. So you're saying that like the fact that this coarse graining operator is quadratic, there is no assumption here. It's like it's gonna be the same for any scalar. Yeah. Okay.
Here, this coarse graining operator depends on what fixed point you choose, and here H is quadratic because the S0 has been chosen to be the Gaussian fixed point.
Oh, okay. Very good. Thank you.
Yeah. So in other words, your RG scheme, the way you divide the fast mode and slow mode depends on what fixed point you are perturbing around, right? So in order to be able to divide fast mode and slow mode and do the coarse graining procedure, you have to first know, you have to have some sense of what is slow and what is fast, okay? And here, they are organized in terms of the free theory. Yeah, and that is reflected in this Hamiltonian, sorry, not in the coarse graining operator, H. Okay, so now going back to this general scheme. So suppose S0 is a fixed point, and then S1 includes the deformation. That includes all sorts of symmetry allowed single trace and double trace operator as well. Then, as I mentioned, the state that includes only single trace operators form a complete basis. So therefore, this state S1 can be written as a linear superposition of state that includes only single trace operator, and little j is the source for the single trace operator, and psi is the wave function defined in the space of single trace source. And then the generating function is now given by this object. So here it is just a S0 inner product between S0 and S1 now is written in this way. So this is the starting point, and then in one step of coarse graining, we apply this coarse graining operator e to the dzh. Okay, so in the previous in the usual Wilsonian RG, you just apply this, and then you end up generating new action, and then you keep inserting new coarse graining operator and just follow the classical flow of the action. But because we identified the space of field theory as a Hilbert space, it's natural to now decompose this new state that you obtain after applying this coarse graining operator as a linear superposition of the basis states again. Okay, so here this is the new state that you obtain after one infinitesimal step of coarse graining, and because single trace states form a complete basis, that state can be written as a linear superposition of those single trace state with some weight. Okay, and then here J1 is another fluctuating single trace source, and then here I have written the weight in this particular fashion, but the details are not important. But here you can mathematically show that it can be written in this way. And then so after one step of coarse graining, the original generating function has been written in this way, where so you basically insert the coarse graining operator between the overlap, and then it is applied to the right, and then it generates a new operator like multi-trace operator, and then that is written as another linear superposition of single trace state J1, and so that's why J1 is summed over, and then this is the corner that controls the fluctuation of J1. Okay, and then if you repeat this procedure, then again you insert the coarse graining operator, and then the new state is written as a linear superposition of the single trace state, and so on. Then that means at every step of coarse graining, you end up introducing this fluctuating source J, and as a result, your original generating function is now written as a path integration for the single trace source, and then there's some weight, okay, that determines some types of action for the source that determines the weight for each path defined in the space of single trace source. So this is what quantum RG is. So therefore, if you do this step infinitely many times and then make the step size infinitesimally small, then your original generating function can be written as a sum over all RG paths. Okay, so it's a path integration for RG paths. But this RG flow is unlike the conventional RG. This RG flow is confined in the space of single trace coupling. Okay, and the space of single trace coupling is much smaller than the full space of coupling. It's exponentially small. And then the price we have to pay then is to sum over all RG passes. Okay, and then this action for the single trace coupling determines the weight for each RG path. Okay, so in a way, the coupling constant or this source are promoted to quantum mechanical variable. Okay, and
so what you're sort of saying is that well, I can do Wilsonian RG, and in Wilsonian RG I'm gonna have like multi traces, and but I don't have to path integrate over couplings.
That's right.
That I can restrict myself to single traces. At the price, I have to path integrate over the couplings.
Exactly. Yeah, that's right. Yeah, that's right. Yeah, and you know, and either way, they are exact. Okay, by construction. So there are just an alternative way of formulating RG. You know, in a sense, quantum RG to Wilsonian RG is what quantum computer is to classical computer, in the sense that you exploit the linear superposition principle, and therefore you can keep only a much smaller set of degrees freedom in your system. So through linear superposition principle, you kind of compute the RG flow of multi-trace operator in a parallel way, in a sense. But the point is that they are exact in either way. Okay, so in relation to holography, here I have been very abstract, but in realistic quantum field theory, some of the dynamical source J's include the dynamical source includes the metric, because there's an energy momentum tensor, a single trace energy momentum tensor, and there is a source for that energy momentum tensor, which is metric. And under this construction, all single trace sources become dynamical variable. You have to sum over those single trace sources, and as a result, metric become dynamical. So therefore, the action you generate in the bulk generically is a dynamical theory of geometry, the metric as well.
So I still have a question about this. So I mean, I think I understood the basic idea, but then like when you have like this new path integral involving path integrating over the sources, the real question is like, is the action that you integrate local, right? Because if it's not, if it's you know, like a very messy expression, then it's not very constructive, right? Because it might be very hard to find principles that govern it.
Yes, yeah. So in general, yeah, so that's a good point. In general, the space of single trace sources are still infinite, and also furthermore, the full space of single trace operators include non-local operators. Okay, so therefore, the bulk theory that you construct are kinematically non-local in general. So, and And in principle, you have to include all of them. Okay, so that's one complication. For general weakly coupled quantum field theory, the dual theory that you constructed in this way is highly non-local kinematically, in the sense that you have to include non-local object. So I will come back to this point when we discuss some concrete example like a large N vector model, which is a weakly coupled field theory. Okay? Yeah. So yeah, that's a good point. So here, the point I was making is that the bulk theory that you construct this way includes dynamical gravity, and then therefore, if you know how to regularize quantum field theory, okay, and if you have a concrete regularization scheme, then through this construction you can construct a regularized dynamical theory of gravity. So that's the goal. If you the goal is to construct some well-defined theory of gravity, starting from well-defined quantum field theory, and hopefully it's easier to do the latter.
And is it easy to see diff invariance to arise, and like diff invariance as a gauge symmetry in this context? In the
no, it's not easy. I think that is the bottleneck. So in order to guarantee that bulk theory that you generate respect the different of invariance, you first need to know how to regularize your quantum field theory in a curved space-time background in a covariant way. Oh. And the difficulty is that we don't know how to do it. Yeah.
Okay.
Yeah. So, but my point is that if we solve that problem, if we know how to regularize a quantum field theory in a fixed but general curved space-time background, that may give us a way to define a quantum theory of gravity in this way.
And so sorry for bugging you.
No, it's okay.
Is it possible sort of to restrict to some subspace of sources? So I mean, of course, like what I have in mind, for example, is that in 1 + 1 dimensional conformal field theory, like a lot of the results for are governed by the Virasoro algebra.
Yeah.
So, like, you restrict yourself like just to the sector in which you have like stress tensors. So like the sources are just like the background metric. Then some progress can be made. On the other hand, like I think there were results pointing out that it's hard to make sense of like pure gravity with negative cosmological constant from the point of view.
Yes. Yeah. So okay. Yeah, that's right. So in general, you cannot truncate to a smaller set of variable in the bulk, because under the Coarse grain, you in general ends up generating all other operators. And then I think one condition that you need to do that is to have a large gap in your spectrum. So if you have in the spectrum of scaling dimension, for example, so if you have only small set of operator with small scaling dimension in your field theory, then that will translate to a large gap in the mass spectrum of the bulk degrees freedom, and then you may be able to say focus on those small set of bulk degrees freedom, and that is properties of your field theories. And in general, you cannot do that, but usually, I guess you need to have some strongly coupled field theory with large anomalous dimension for that to happen. Yeah. So actually, the second part of the example is a toy example. If you assume that there is a field theory that has only energy momentum tensor, and if you assume that all other operators have a very large scaling dimension, and in that case, the bulk degrees freedom involves only the metric. Okay, then you may hope to obtain some simple the bulk gravitational dual. Of course, the real question is whether such theory, quantum field theory, exists or not. Yeah. Yeah. So so that was the general discussion. And we move on to some examples. So first, let's consider a n-component vector model. So phi is n-component complex scalars, and this is familiar field theory. And as I mentioned, since I don't know how to regularize this field theory in general curved space and time, I'm going to use lattice regularization. So here, in this here, I represent space-time lattice, and then at each point in space-time lattice, I have this n-component scalar field, and some full action. But I'm going to choose my IR fixed point action to be this ultra local term, mass term. So this IR fixed point is the this S naught is the fixed point action for the gapped phase. So when mass is non-zero, if the system is in the gapped phase, then we know in the long distance limit the correlation length goes to 0, and it's that the mass term is indeed the fixed point action. So here I have chosen S naught to be this ultra local fixed point action for the gapped phase. Of course, this my guess may or may not be correct. Okay, so and we will see that this will show up in an interesting way later. And then S1 includes all other terms. In particular, it includes the gradient term. So because I'm using lattice regularization, the gradient term is expressed in terms of some kind of hopping term. Okay, so Tij is hopping that connects different sites in space-time lattice that will translate into the gradient term in continuum. And also I included some quartic interaction. Okay. And then the partition function or generating function can be written as the overlap between two state. S naught is the state with this gapped fixed point action, and then this T naught is the state with this hopping amplitude Tij with this quartic interaction with some fixed lambda. Okay. So here
you don't allow higher order terms like six-stick or whatever.
Yeah, we could allow them. Yeah, and they will be generated in any way. So okay. Yeah, and but yeah. Okay. I think short answer is we could allow, but here for simplicity, I just include the quartic term.
Okay.
Right, and then so here what I'm doing is that I have some full theory like this, some value of hopping, some value of m, some value of quartic interaction lambda, and I don't know yet what fixed point this full theory flows into. I don't know what the actual dynamical gap of the system is, and here I'm guessing that maybe this theory flows into a gapped phase in the IR. That's why I have chosen S naught to be my fixed point action. And all other thing is now viewed as a deformation. Okay, but as we know, if T is big enough, the system doesn't necessarily go into the gapped phase. They may be a critical state, for example. and depending on which phase the full system is in, the RG flow that we will get will be very different. So, and then because the fixed point is chosen to be the gapped state, and in particular, this gapped state S0 is a direct product state. In other words, there's no as a wave function, this doesn't have any entanglement between different points in space and time. So here I'm talking entanglement for this space-time state. But you can generalize the notion of entanglement for spatial state in this setting as well. And in this direct ultra local action corresponds to the this trivially gapped state, and therefore the coarse graining operator that leaves that ultra local state invariant is also ultra local. So this H, this Hamiltonian, it's like a essentially harmonic oscillator, sum of harmonic oscillator at each site in space-time lattice, and one can show that S0 is the ground state of this operator with the zero energy. So therefore, it is invariant under the coarse graining operator. And then we insert this e to the minus zh between this overlap to generate the flow of the state on the right, labeled by this hopping amplitude. And physically, what this coarse graining operator does is to gradually project your state to the direct product state. And in other words, it gradually removes the entanglement present in space and time. Okay. And then again, if you insert this coarse graining operator repeatedly as before, then your generating function can be written as a path integration for this source for the single trace operator. So in this case, the single trace operators are this bilocal operator, phi I star phi j. Okay, so this single trace operator is and therefore this state labeled by different values of t form a complete basis. So therefore, the generating function can be written as path integration for that for Tij, and then that path integration picture can be also cast into the Hamiltonian formalism, and then there will be some Hamiltonian for T that generate the path integration, and this is the Hamiltonian, written in terms of this quantum operator T and T dagger. So here T was a single trace operator, right? A source for the single trace operator, and we said the generating function is written as a path integration of this T, and therefore in the Hamiltonian formalism, T become a quantum operator. Okay, and then this is the Hamiltonian, quantum Hamiltonian for that written in terms of T and T dagger. And here, from the original field theory point of view, Tij measures the strength of the coupling or hopping between, or connectivity between site I and J. And now that coupling has been promoted to quantum operator. And in this language, T dagger is a quantum operator that create some quantum of connectivity between site I and J, and Tij is an annihilation operator. Okay, and this Hamiltonian describes how this this connectivity evolves quantum mechanically. So details of the term in the Hamiltonian is not important, but this is something you can derive explicitly. And
And yeah, okay. I mean, in this Hamiltonian, like maybe it's like the subject of the next transparency. Like, can you see some structure? I'm like, I mean, apart from like the obvious thing that they're like, you know, like linear, quadratic, cubic pieces, but like, is there some structure to it?
Yeah. So the most important piece is this last term, the cubic term. There's indeed an important structure. So first thing to note is that so now this bilocal object Tij has been promoted into the dynamical variable. So here Tij is dynamical variable in the bulk, and then in the Hamiltonian, there's no hoping term for this bilocal object. In other words, there's no term in the Hamiltonian that describes that Tij hopes to Tik. If there was term like that, that would mean that, you know, some connection between Ik become longer connection Ik. But there's no such term in the Hamiltonian. Instead, there's a cubic term like this, and this cubic term describes the process where two connections between Ij and Jk merge into a longer connection between Ik. Okay, so and this has some important implication, because in order to be able to define quadratic term like this, the hoping for this bilocal field, then you should have some sense of distance between psi k and j, because here bilocal field is hoping from one end from k to j. But there's no in gravitational theory there should be no pre-imposed background that sets the distance between k and j. That's why the Hamiltonian doesn't have this kind of quadratic term, but instead you have a cubic term. But suppose at the dynamically, suppose this bilocal field acquires some expectation value in the bulk, and then this cubic term now generate a quadratic term for this bilocal field like this. And then in this case, if Tjk acquires some expectation value, then that generate now quadratic hoping term for this bilocal field. And now this term describes the process where Tij connection propagate into or hop into Tik, and then the hoping amplitude is proportional to the expectation value of the bilocal fields themselves. So in other words, the notion of distance between j and k is not predetermined. It is determined by it is determined dynamically. It is determined by the expectation value of the bilocal fields themselves. So in this sense, there's a sense of background independence, and this Tij encodes the information about this distance between different sites. Okay, and it determines the metric. And here, this Hamiltonian that is written for the T describes the evolution of that quantum geometry under coarse graining. And so in the full theory is quantum mechanical theory, but in the large and limit, you can do the path integration for this Tij can be replaced by the saddle point approximation, and this is the saddle point equation. And in this case, you can solve the saddle point equation exactly, and this is the solution. So this is not very illuminating. Let me just explain in picture what this solution means in different phases. And once you have a saddle point solution, then you can think about fluctuation away from the saddle point. So here T bar is the saddle point in the bulk, and then T tilde is the fluctuation away from the saddle point. And then once you have a saddle point, you can expand your action around the saddle point, and then you can write down the action for the fluctuating mode. And then this fluctuating mode will have some kinetic term that allows them to propagate in the background of geometry set by the saddle point themselves. And then from that, you can read the metric in the bulk.
And let's see. So it's this anti-symmetric component is like it's a field of what spin?
Yeah. So this must be a field with odd spin.
With odd spin.
There are also symmetric components as well. Yeah, but here equation motion for this odd spin is, in this case, is particularly simple. So I just focused on that to read the geometry. But you could read the geometry from equation motion for other modes as well.
Like what I'm a bit like surprised about is that this differential operator does not have like any contractions with indices carried by this field, right?
Sorry, which differential operator?
So you have like this differential operator, including like the derivative with respect to z. Like,
okay, yeah.
This guy is not contracted with indices in T tilde, right? So like these are all like.
So let me see. So suppose, so here in this cubic term, suppose T has some expectation value, okay?
Yeah.
And then we consider fluctuation away from that saddle point.
Yeah,
and
then, I understand, yeah.
And then so out of this cubic term, suppose this last one is replaced by the saddle point guy, and then this two is the fluctuation, right?
Yes.
And then this term describes in the continuum limit, describes some gradient term because the psi j is changing into psi k, right?
Yeah.
And then the range of that, the coefficient on the differential operator is proportional to the saddle point value of tjk. So what I did here is this tjk is a bilocal object, but now I can do the gradient expansion. Okay.
Okay. Very good. So I I think my confusion was that like I thought about expectation value of tjk as the metric, but you're saying that it's not the metric. What I want to do is I want to derive the equation of motion for fluctuation, and from this equation of motion, I want to derive the metric.
That's right. From the coefficient of the gradient term, I can read the information of the metric.
Yeah. Okay. Agreed.
Yeah. So it's like a bilocal. There are two feet. This field has a two coordinate, and then here this first term describes the motion of one feet, and this term describes the motion of the other feet, and they can propagate in space and time, and the coefficient in front of them is determined by the saddle point solution of T, which then determines the metric in the space and time.
Oh, I see. Super.
Sung-Sik, do you think you can wrap up in about 5 minutes or so?
Yeah. Okay, I will do that. Yeah.
Okay.
Okay, suppose, so this is some cartoon picture for the saddle point solution that I was saying. So suppose initially at some UV scale, suppose I turned on only some nearest neighbor Tij like this at the figure bottom, okay? And then what happens is that as we go to deeper in the bulk, because of this process where the short range Tij merge into longer range Tij. So as the coarse graining Hamiltonian tried to remove the entanglement, on the other hand, this entanglement spread to a longer range. So that's why you generate some longer range Tij, but at the same time, the amplitude of Tij goes down under this coarse graining. And if the full system is in the gap phase, what happens is that although the range of the hopping or range of entanglement increases, it doesn't increase forever. It saturates, there's some bound on how far the entanglement spread. The solution, you can read this from the exact solution, and then it doesn't increase further. And then as we go further down, all the entanglement disappears, so that the state S1 can be projected to the direct product state smoothly. And so I'm referring to this. So this is a coarse grain operator applied to this state associated with the deformation added to the ultra-local theory. And then if the full system is in the gapped phase, if the gap is non-zero, then in the large Z limit, this state is become a direct product state. Okay, and then in that case, from the equation motion I mentioned, you can read the bulk metric. So here's little delta is the gap of the system, and you can explicitly derive this metric. And if the system is gapped, then the proper size, proper distance in the radial direction is finite, okay, as is expected. On the other hand, if system is in the gapless phase, then of course from the action it's very hard to tell. It's just almost same action with slightly different values of Tij. So in prior, you don't know whether the system is in the gapped or gapless phase. But the RG flows knows that. So if the system is in the gapless phase, under coarse graining, the Tij become local entanglement disappears, the amplitude of Tij goes down, but at the same time, the range of Tij increases, and it increases without bound. It becomes bigger and bigger. And although you can keep removing the local entanglement, the entanglement spread to larger and larger distance, so that in the thermodynamic limit, you cannot completely project your state to the direct product state at any finite depth. So that's what happens. And so in a sense, the range of entanglement, range of Tij diverges as Z, the RG distance Z goes to infinite. So in a sense, there's some kind of critical point at Z equal infinity, like a second order phase transition, but this is like a phase transition as function of the length scale. So as the RG length scale increases, your renormalized hopping range of hopping become larger and larger, and it diverges at in the infrared limit. So it's as if there's a critical point at Z equal infinity, and it turns out that that critical point precisely represent the Poincare horizon that arises in this in the bulk geometries, and you can derive this geometry, which is the ADS geometry. And the origin of the Poincare horizon that happens at Z equal infinity is actually it can be viewed as an obstruction that we cannot project our entangled state to the direct product state. Okay, yeah. So let me skip this part. So this the last part was this toy model that I mentioned briefly. If you assume that if your field theory has only energy momentum tensor but nothing else with finite scaling dimension, then you can show by applying quantum RG that the dual theory is actually Einstein gravity up to second order. So let me just wrap up. So just from RG point of view, quantum RG is an alternative way of organizing your RG. The advantage is that you keep only a very small set of coupling, but in general, there are still infinite set of coupling called single trace operators. But then you have to sum over all RG paths for those subset of couplings. So in general, that's not very useful because the RG problem is another difficult quantum problem. But in some large n limit, the fluctuation of the RG paths become small, so that you can solve that using classical equation motion. But still, the difficulty usually lies in the fact that you still have to keep infinitely many source for the single trace operator for if you want to be exact, right? So, but the hope is that in strongly coupled field theory, you may be able to keep only a small number of field in the bulk, and then may corresponds to some simple gravitational theory. Okay, so I will stop here. Yeah, thank you for listening.
Maybe we have time for one more question. Anybody? I don't remember how to.
Well, so also like this notion of the notion of entanglement appeared as an important notion for the geometry, right? So like for the function.
Yeah.
And can one try to learn something about this approach, like using, say, methods that utilize entanglement to represent quantum states? So I mean, tensor networks. Yeah,
that's right. So all I said can be actually viewed as an evolution of tensor networks under coarse graining. So I didn't attempt to explain in that language, but precisely as you said, this this picture, the evolution of this the single trace operator can be understood as an evolution of some tensor that is generated under coarse graining, and I think maybe one related comment is that here the tensor that you have to include to be accurate have all sizes. So it's by no means a local contractions of tensors. So there's no pre-imposed local structure. Okay, so you have a very messy network of non-local tensors, and then but the real locality is determined dynamically only after you solve the equation motion. That equation motion determines the strength of tensors at different size. Okay, so only after that some notion of locality emerges. But kinematically, the tensor network you have in the bulk is highly non-local. And I think
so. You're saying that kinematically, the entanglement content of the network can be arbitrarily large. In the sense that entanglement can be like arbitrarily long range, and its strength can be very large.
So let me say so there's a tensor of all sizes, and then strength of the tensor is the dynamical variable.
Yeah, I understand.
And then depending on the value of the say in this case Tij, the strength of the tensor, the amount of entanglement changes. Okay, so when I say kinematically non-local, the network of tensor is non-local. But now the strength of tensor for each size is a dynamical variable. There's some action that controls the strength of each tensor, and then we have to sum over all possible the tensor strengths. So that is basically the bulk path integration. And then once you solve the equation, say in the large and limit, if you can use the saddle point approximation, and once you solve the equation motion, then that fixes the strength of tensor of each size. Only then you can ask what the amount of entanglement, what is the locality, etc. And then what I'm emphasizing is that the locality is what emerges dynamically. It's not something you impose kinematically.
No, I understand this. Yeah, like another quick comment is that like what I noticed in like when you were taking is like the fixed point for your RG, like what you took is like a theory that is ultra local.
Yes.
Like the theory, and this is not something that I mean, it's like an infrared fixed point, right? But like typically that's not what you do. Like in field theory, like in field theory, you take like a scaling variance fixed point, like the relativistic CFT.
Yeah. Yeah.
Like,
so
in fact, like this ultra local fixed point is taken as like as a UV behavior of a theory in this Chimera approximation. So I feel like your student worked on this, I think.
Yeah.
Right?
So yeah. So here ultra local fixed point is a guess for the IR fixed point. And then if my guess is wrong, this is what happens if I am in critical phase. Okay. And then there's an obstruction. You cannot smoothly map your full action into ultra local action, and that obstruction arises as horizon as an ADS geometry in the bulk. So the final answer you get, the final geometry, is not always the ultra local. So ultra local is my guess, but the answer you get is actually the geometry that is for the critical state if your system is actually in the critical state, in critical phase. Yeah.
And the last question, and I'm gonna let everybody go. Sorry about this. It's like, I mean, like your picture is very beautiful, and like as far as I can see it, like it okay, apart from the obvious issues of like UV regularization and so on and so forth, like it looks very convincing. But it's like very hard to make exact calculations, right? So can you envision a case in which there's like some extended symmetry? So for example, some integrable structure in a field, and this integrable structure allows you to constrain, the bulk, so that like actually, like you see, say, some notion of string theory.
Yeah, I think that's an interesting. Yeah, I think that's an interesting direction. So far, only theory that has been solved exactly in the large and limit is this vector model, both fermionic version and bosonic version. Some large and generalization of bosonic and fermionic Hubbard model like that. But it will be interesting to find some other examples that is non-trivial but can be solved in this method, and maybe if there's some integral structure, then may be helpful. But I haven't thought about that in that direction. Yeah, but that's a good comment.
Yeah, thank you.
Okay, yeah.
Let's thank the speaker again.
Thank you very much.
Thank you.
Yeah.